Okay, so here we are at Objective 3 of Section 1.1 of Stewart's Calculus. Two topics having to do with functions. Those are symmetry and increasing and decreasing functions. If a function f satisfy the equation f of negative x equals f of x, for every x in the domain of f, then f is called an even function. Okay, so it's not only numbers that can be even or odd, functions can be even or odd. And that's the equation to remember for even. For instance, f of x equals x squared is in the category of even functions because f of negative x, which is the square of negative x, which actually turns out to be the same thing as x squared, because negative x times negative x is the same as x times x, which is x squared. That's f of x. And so because these two things are equal, it's an even function. The geometric significance of an even function is that its graph is symmetric with respect to the y-axis. So here's an example. This is not f of x equals x squared. It's just some even function. And you can see how f of negative x is equal to f of x, because here's an x, whatever number it is, the negative of that number is, the same distance to the left, and the f of's, those are the heights of the functions, and those heights are the same when we're to the left or to the right, the same distance. So we have y-axis symmetry for every even function. This means that if we have plotted the graph f of x, plotted the graph of f for x greater than or equal to 0, so just on the right, okay, just over here, just on the right, not on the left, but then we can obtain the entire graph by reflecting this portion about the y-axis or folding it over the y-axis. Odd. For odd, f has to satisfy f of negative x equals the negative of f of x. Okay, so again, the definition has to do with what does f do with negative x as an input. In the case of the even function, it just returned f of x, but in the case of an odd function, it's the negative of f of x for every number x in the domain. For example, f of x equals x cubed is odd because f of negative x, which is the cube of negative x times negative x times negative x is the negative of x cubed, which is the negative of f of x, because f of x is x cubed. Well, because these two things are the same, f of negative x is the same as the negative f of x, the cubing function f of x equals x cubed is odd. And of course, I don't suppose you'll be surprised to learn that the fact that the exponent is odd is not a mere coincidence. We had x squared, an even exponent, and that turned out to be an even function, and now we've got a odd exponent for this odd function. Not a coincidence. That is not to say that you know it just from the exponent immediately. There is a rule like that for polynomial functions. Actually, I'll just say what it is. If it's a polynomial function, now that greatly restricts the class of functions that we could be talking about as far as even or odd is concerned. But if it's a polynomial function, If all of the exponents on x are odd, then it's going to be an odd function. If all of the exponents on x are even, then it's going to be an even function. So that's a rule that we're just throwing in there that happens to be true. Remember that constants are even degreed terms. Right? 5 is that's of even degree because it's 5x to the 0, and 0 is an even number. What about the symmetry of an odd function? The graph of an odd function is symmetric about the origin. Okay, symmetric about the origin. So in the case of the cubing function, okay, it has origin symmetry, meaning you could take any point on the graph, you could go to the origin, the object of symmetry, so it's point symmetry, not line symmetry for odd functions. Take any point on the graph, go to the origin, go same distance, same direction beyond it, and you end up with another point on the graph. That's true for any point on the graph. We could also think of it as if we already have the graph of f of x for x greater than or equal to 0, just to the right, we can obtain the entire graph by, it's actually rotating through 180 degrees about the origin. So here's an odd function, and we're going to simulate a rotation of 180 degrees through the origin. And so we're going to spin this thing clockwise 180 degrees. And so focus on just this part to the right, and watch what happens as we look at just that part and we rotate through 180 degrees through the origin. Okay, and it ends up landing on the other part of the graph. We end up getting the full graph with the rotation. So if we already have the graph of f, for the right part of it, to the right of the y-axis, we can obtain the entire graph by rotating 180 degrees through the origin. Once again, watch that right part of the blue. Rotating, 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 rotating. That's 180 degrees right there. And now we've got the whole graph after the rotation. Determine whether each of the following functions is even, odd, or neither. Okay, so remember what these things mean. Even means that f of negative x is f of x. Okay. And odd does something else with f of negative x. F of negative x is the negative of f of x for odd. And then it could be neither. So we're going to see which one of those things is true. The basic strategy will be to see what happens with f of negative x, because even, odd, they both have that in the definition. see what happens with f of negative x. Well, for part A, f of negative x is the fifth power of negative x plus a negative x. Now, is that the same thing as f of x, or is that the same thing as the negative of f of x? Well, let's simplify, see if we can find one of those forms. We could think of the first term as the fifth power of negative 1 times x to the fifth, because the power of a product is the product of the powers. Well, that's just going to be the negative of x to the fifth minus x, but we could factor out a negative, and what's left on the inside is actually the same thing as f of x. Right? That's the f of x that we were given, and we've got the negative of it now. And so actually, f of negative x is the same as the negative of f of x. So these two things are the same, making f an odd function. Well, let's see what happens with g of negative x. Let's see what happens with g of negative x. Now, g of negative x it really shouldn't be written that way. G of negative x really should be written this way, at least in the first step. G of negative x is 1 minus the fourth power of negative x. But of course, an even number of negative factors is positive. Negative x times negative x times negative x times negative x. We will get rid of this here because that's just not even right. Is positive x to the fourth. Negative x times negative x times negative x times negative x is positive x to the fourth, which is what we're subtracting from 1. Well, that's the same thing as g of x. And so g is an even function. Let's try h of x. What does that do with negative x? Well, that gives us 2 times negative x minus the square of negative x. And again, that's unfortunate. This is actually not even right. So let's fix the slide here. H of negative x, if you look at h of x, if you look at h of x up here, h of negative x is 2 times negative x minus the square of negative x. So we're replacing x with negative x. Well, that is 2 times negative x minus x squared, which is the same thing as negative 2x minus x squared. And we might want to do the same thing that we did with f, which is to factor out a negative. Negative of 2 plus x squared, 2x plus x squared. But that's not h. H is 2x minus x squared. So we can't say that h of negative x equals the negative of h of x. Okay, so we can't say this here. It's not an odd function. And this is not the same thing as h of x, because h of x has positive 2x, this has negative 2x, and so it's also true that h of negative x is not equal to h of x, so it's not even either. We conclude that h is neither even nor odd. And so the graph of h, we'll just start with h over here, doesn't have symmetry with respect to the origin, and it doesn't have symmetry with respect to the y-axis, because it's not odd and it's not even. Okay, obviously it doesn't have y-axis symmetry. It doesn't have origin symmetry either. It's not as if you could take any point on the graph, go to the origin, go same distance, same direction beyond it, and get another point on the graph. But the even function g does have y-axis symmetry. We could fold the right half over the y-axis and or reflect it and get the whole graph. And for f, we could take the part that is to the right and rotate it 180 degrees through the origin and get the entire graph. Or another way to think of it for an odd function like f here is that we could do the double fold. We could take the part that's in the, well, we could take any part of it, but just think of the part that's in the first quadrant. We could fold that over the x-axis and fold the result over the y-axis, and you would get the rest of the graph. So that's another way to think of a geometric interpretation of the oddness of a function. Increasing and decreasing functions. Here's a function f. It's said to be increasing on the interval AB, decreasing on the interval BC, increasing again on the interval CD. Okay, so on the interval AB, okay, so right in here, it's increasing. So the little car is going uphill. Okay, little car is going uphill. Car is still going uphill because we haven't gotten, as we go right to left, you know, we haven't gotten to B yet. As we go right to left. So little car is still going uphill. But then, okay, this will be a challenge to draw. Little car is going to start going downhill. From B to C. So until we get to C, we're going to be going downhill. But then he's going to turn around and start going uphill again between C and D. Car's going uphill between C and D. Notice that if x sub 1 and x sub 2 are any two numbers between a and b, with x1 less than x2, then the height, f of x1, will always be less than f of x2. So if we're in this interval here between a and b, okay, we could pick any two numbers, x1 and x2. Maybe x1 is here. Of course, x1 has to be less than x2, so it's going to be to the left. Less than x2, f of x1, okay, so f of x1 is going to be below f of x2 for an increasing function always, or a function which is increasing on an interval I. On that interval, we're always going to have f of x1 less than f of x2. A function f is called increasing on an interval I. So we could have an interval I, which is the interval a to b, for example. F of x1 is less than f of x2 whenever x1 is less than x2 in the interval I. For the definition of decreasing, all we do is flip this one inequality symbol, and now we've got the definition of decreasing, which is understood analogously to the definition of increasing. In the definition of an increasing function, it is important to realize that the inequality f of x1 less than f of x2 must be satisfied for every pair of numbers x1 and x2 in I. Right? We could take any x1 and x2 with x1 to the left of x2 in some interval I. Well, you can see from figure 23 that the function is increasing on 0 to infinity, but it's decreasing on negative infinity to 0. Car goes downhill until as we read from left to right, the car goes downhill until we get to 0, then it goes uphill.